Okay, I guess we'll go ahead and start. Hi, everyone. Thank you for joining us today for our ALS Webinar Wednesday series. My name is Alex Yao. I'm the marketing coordinator for ALS North America, and I'll be facilitating today. Just a few helpful notes before we begin. If you're having technical issues with our webinar platform or any questions, you can type your message or question using the chat function at the bottom of the screen. And you can also select the hand icon to notify me of your status so I can assist you. All questions regarding the webinar material will be answered at the end of the presentation, where we'll have a short Q&A session. Our presenter today is Ron McLeod. Ron McLeod is the Director of Special Chemistries and Air Toxics, Eastern Canada, and has a Bachelor's Science and PhD in Chemistry from McMaster University. He also has 34 years of management experience in the environmental laboratory business, including with Xenon, Philip Analytical Services, and Access Analytical, including some 30 years of expertise in air toxics and HRMS analyses. The ALS Burlington Lab, which started in 2005, was based upon a business plan for HRMS and air toxic services authored and presented by Ron. Ron, thanks for taking the time to deliver this presentation. I'm going to go ahead and turn it over to you.
Appreciate it. Thank you. And I thank everybody for their time. I hope that I can provide some value for that time. Did want to go over and introduce to you classical and emerging stack and ambient analytical methods. Our ALS Burlington facility is due to our initiation and continue to be specialty in air toxics and in high-res MS analyses. And in the environmental network for ALS, there are 4 labs in North America that specialize in air analyses. 2 of them in Cincinnati and Salt Lake City specialize in industrial hygiene methods. And ourselves in Burlington and Simi Valley specialize in ambient and stack methods. Now, there's a difference between the 2 of us. We specialize in Burlington on semi-volatiles and metal analyses, whereas Simi Valley specializes in VOCs and canister analyses and a plethora of different volatile methods. So there's very little overlap, but still different labs in our network do some of these methods. But these are the labs that are specialized in these areas. I wanted to, again, give you an introduction to ambient and stack methods, the terms, what sampling trains are all about, ambient sampling devices, and also I'll give a brief introduction into 2 new and what I perceive as hot methods for stack emissions, and one of them has perfluorinateds, and the other is sources for natural gas feeds into the natural gas networks. First of all, I'm going to bore you with some issues of terms and try to make sure that people have a level understanding to go through this presentation and understanding going forward. The item on the bottom, the last one, the sampling trains, is what I'll talk about first. Sampling trains in stack emissions refer to the connective set of glassware or even stainless steel or Teflon parts that constitute a sampling, and that can include a probe, nozzle probe, say a filter, and maybe impingers or something along those lines. And after that, an umbilical cord down to pumps and flow meters and so forth. So that's what a sampling train refers to. It's really from the stack emissions. The next issue, the 4 items in the red are kind of related, are quite strongly related. Particulate versus non-particulate bound, what's a VOC, what's a semi-volatile, and isokinetic versus non-isokinetic sampling, all very heavily correlated, and even the metals, volatiles versus non-volatile metals. A lot of the analysis targets are particulate bound, but whether they're particulate bound or not is dependent on the temperature of the stack, on the boiling point of the targets, and the affinity to the particulates. So this is what in the stack methods differentiates between VOCs or volatiles and semi-volatiles on the organic side, whether or not they're particulate bound. And really the definition therefore of volatiles and semi-volatiles depends on your application and even method. And it goes so far because of it can be temperature and particulate type related. It can even be source related. In the stack methods, there's a general deviation by boiling point, and a volatile is generally considered one less than 100 degrees Celsius or up to 132 degrees Celsius boiling point. And that is the general demarcation between items being particulate versus non-particulate bound. Now, where does isokinetic sampling and isokinetic and non-isokinetic correlate to? Well, in order to get a representative sample, and if targets are particulate bound, then from a stack, you need to be sampling isokinetically. Isokinetically means that where you're taking your sample into the probe needs to have the same linear velocity going into that nozzle as the stack linear velocity around it. So isokinetic sampling is basically you're sampling at a sample rate that matches the flow of the stack. And the reason for that is that if you're not, then the flow around the nozzle is perturbed, and therefore the particulate, which has a momentum, is deflected away from the nozzle. So in order to get a representative sample, you need, for particulate bound materials, it needs to be isokinetic in the sampling approach. And this, of course, relates even to volatile and non-volatile metals. Now, when sampling, a stack sampling, I'm sure you're familiar with the term platform and ports, but around a large stack, you'll generally see a sampling platform. And you'll see this ring when you're looking to drive by a stack, you'll see this ring with usually with some kind of ladder to get up to it and a railing. And that's where the stack samplers go up to do their sampling. And the ports are in the side of the stack in order to get the probes in order to do the sampling. Points of impingement, again, this relates to being able to get a representative sample. And the sample near the stack wall and the flow rate near the stack wall, and even the constituents and the homogeneity or non-homogeneity is different from the side of the stack to the center of the stack to the other side of the stack. So when they're sampling, not only do they have to get a probe into the stack, they also have to sample at several different points. And so in general, they're sampling, they stick their probe in, and they sample at different points across the cross section of the stack. Well, then they do that all the way across the stack, and that represents half of the sample. And then they do something called a traverse. They shut off the train, they shut the pumps off, they seal off the train, and they move the train out of the sampling port and rotate it to a port that's 90 degrees away to the other side. And then they continue their sampling and do points. So they're basically doing points across an X, across the two diameters of the stack in order to make a sample. The front and back half has to do with the definition of front half is everything up from the probe up to the filter and including the filter. The back half is after the filter. A cyclone is something used in both stack and ambient. And it's used in order to by cyclic design and size in order to drop out different size particles. So it's a way in which you can collect only PM 2.5 or PM 10, or you could, without a cyclone, get the total particulate. Wet versus dry stacks. Now, this is the second area. Now, we talk about air sampling, and there's really three areas. There's industrial hygiene, there's ambient, and there's stack. And this wet and versus dry issues is another unique issue associated with stack testing. I've gone through the isokinetic sampling, but a wet source is one typically like a combustion source where the level of moisture in the source is quite high. And the definition of a wet stack is one where when you drop the temperature of the stack gases down, you get a condensate. And there's a high percentage of it. Now, stacks don't have to be combustion sources. They can be dry kilns. They can be even vent stacks of all sorts. But stack testing methods need to accommodate when their sample is at a source where it's a wet stack. And I'll get into that in a little bit later on the sampling train design. Now, classical stack methods. I'm not expecting everybody to be able to list these methods. There's on the left-hand side, there's the targets. And on the right-hand side, there's some of the methods appropriate for them. I have EPA, I have California Air Resources Boards, I have Environment Canada method references, the EPA SW46 reference methods. So some of these come from different sources in different areas. But we in Burlington do all of these methods, includes dioxins, PAHs, PCBs, PAHs, and PCBs. We do by both low res and high res, dioxins exclusively by high res. Other semi-volatiles by low res. We do VOST, which is a volatile method, which includes sampling. It's a stack method for sampling VOCs onto solid sorbents. We do multi-metals and mercury and anions is listed. That's actually HF, so acid gases, HF, HCl, HBr, Br2, Cl2 are included in these methods. The method 26 and 26A are EPA methods. One of them is isokinetic, the other is non-isokinetic. Gives both options for those targets. Ammonia, CTM, or conditional test method 027, we offer filter particulates. Method 5 is an out-of-stack filter method. Method 201A is an in-stack method, stack method. Condensable particulates, which is after the front half, after the filter, whatever condenses past that. The EPA method now is at method 202, and the Environment Canada equivalent is method reference method 55. On the ambient side, here's a listing of typical methods. The ones in gray are all ones that we offer. The ones in red are offered by other labs within the network, including Simi Valley. And so we have a way of providing comprehensive both stack and ambient methods and throughout our network. Again, most of these are, the first top are the TO methods, toxic organics, and you'll see in pesticides and PAHs, there are both high vol and mid vol options. The high vol refer to methods that are using a TISH type sampler, which typically does about 300 meter cubed of sample size for over 24 hours. The mid volume are TO10A and there's an IP8 method. These are smaller traps and smaller volumes, and I'll have more on that specifically on what sampling size you need from the pH and the dioxins a little bit later. On the bottom, we have TSP, total suspended particulates, so particulates methods. including PM10 and PM2.5. The IO in inorganic compendium methods, we offer some of those. We also offer the metals and particulate from the Teflon type filters, method 212. The Teflon, which are 47 millimeter filters, require microbalance, and we have a special balance room for doing those. The other particulates are done off of quartz filters, the ambient off of 8x10s, the stack off of filters, which are generally 82.6 millimeter discs. They're done generally off of a 4-place balance, but the M212 is because it's a smaller filter and smaller flow rates, requires the microbalance for that testing. Now, to give you an image of what the trains look like, this is actually an image of the multi-metals train, the method 29 train, or also 0060 train. And it's very simple, similar to the method 5 train. The method 5 train is for particulate. The difference between the trains has to do with this area and what impingers are there, but otherwise the trains are the same. And you'll see here's the nozzle sampling location. This is to represent the probe. It's shown to have a jacket. It's a heated jacket. This probe then gets pushed in and out of the stack, along with, represents the pitot tube. The pitot tube, which is put alongside of the sampling probe, is to measure at all times the stack flow, so that at every point you're able to measure stack flow and match the flow into the nozzle from isokinetic sampling. So down the train, we go to the filter housing, which generally has an 82.6 quartz filter in it. This is a heated zone, so this is heated to 110 or 120 degrees Celsius to ensure that there's no condensation on the filter. Then afterwards, there's a series of impingers. In the method 5, it's just a knockout and a couple of water impingers to capture the moisture. In the method 29 here, you've got nitric peroxide to get most of the metals go past the filter, but also permanganate sulfuric impingers in order to capture elemental mercury and some mercuric chloride. Past here, and this is what's up on the stack. This is where this is on the platform that's on the stack, and then there's generally an umbilical cord that goes down this area here of the pumps and the meters and so forth. They're generally in a trailer where people are monitoring the pitot tube flow measurement here and ensuring that the vacuum here matches, and the flow rate into the nozzle matches what the pitot tube is measuring as far as the flow up the stack. So that gives you an idea of what the trains look like. I've also shown you a slightly different approach, and this is sometimes called a modified method 5 train or a semi-volatile train. It's in common to the dioxin methods and the carb methods for PAHs and PCB and dioxins. So it's a general semi-volatile approach, very similar in structure to the other trains that I was showing, except the types of impingers or what the content in the impingers in this section here. This section here is where the gases that are drawn in here go through a condenser, drop the temperature, and of course, if there's any moisture, it drops the moisture out. And so then the gases and moisture go percolating through the X8E trap, which captures a good deal of the SVOCs. In general, most of the SVOCs are captured on the filter and in this region here. But beyond here, there's also a dry knockout and a couple of water impingers. Water impingers for the EPA methods. The Environment Canada version uses ethylene glycol and water. Now these trains, whether the metal trains or semi-volatile trains, each of the different components get recovered by a strict protocols, and those components get sent to the lab for analysis. So, for example, the probe and nozzle get rinsed. For organic trains, it'll be organic solvents. For method 5, it's acetone. For method 29, it's nitric acid. The filter gets recovered. These areas, the glassware gets rinsed. The X8E trap, if there is one for semi-volatiles, gets taken out and sent also to the lab. And then the impinger contents get recovered appropriately. Those get bottled and sent to the lab. The before was what it looks like in diagrams. This is what it really looks like in a real stack world. And you'll see here, here's a probe. There's the port in the side of the stack. You've got the huge stack here. So you'll see that the train is actually suspended on a rail here, which fortunately for the testers takes most of the weight. So just pushing that in and out is how they do their points of impingement. And of course, they take it out and then they have to rotate all of this huge piece of equipment across 90 degrees to the other port and do their traverse and do the other portion. Now, I think in this, the chilled portion of the impingers is down here. You'll see it in this area here. And so there's what the impingers look like, and this is the impinger boxes. And so this is again part of the process. You'll see that the port has been covered up to protect the staff from emissions after the sampling port has been vacated. So that's what it really looks like in the field as far as stack testing. And again, you'll see these cords and umbilical cords, which would go down to usually a trailer. It looks like this is a stack on top of a rooftop. That's my guess. And a little bit unusual that the port's so close to the roof, but that's that particular source. Here's an example, pictures of some of the typical ambient sampling devices. The device on the left here is a Tisch sampler. This is a cover roof, which is like a pyramid. And you'll see two hinges here that just flips down to cover and yet allows flow up and around the cover into the sampling. You'll see different types of options as far as sampling heads. This sampling head is the metals particulate type sampling head for an 8x10 quartz filter. This is the semi-volatile sampling head for the TO9 dioxins or the TO13 PAHs or the TO4 PCBs and pesticides. There is a filter that goes in this section here, which is about a 102 centimeter or millimeter filter. There's a glass cartridge with the puff or resin or puff and resin cartridge that goes in this bottom section. So these are different sampling heads that go into this type of device, sampling device. You'll see a pump down here. This takes a 110 or 220 power timer here in order for it to automatically start and stop in your 24-hour location, wherever you're doing it. This item here on the right side is the other type of ambient sampling option. This uses a 47 millimeter Teflon type filter. So this is the M212 type method for doing particulates and or metals. Can include a cyclone so that it would capture only say PM 2.5 or PM 10. These type have the advantage that although it's a lower flow, it allows for battery sampling for 8 or 24 hours And so this is also quite popular, especially in remote locations. The lower flow means that the filters have to be done on micro balances rather than on four-place balances. Now, this slide is just a dump of bits of information that I thought was important to pass on. And if you remember on the first item, I talked about high volume versus mid volume sampling types, the high volume about 300 meter cubed. And if you are analyzing for real toxic quality, to meet the sorts of ambient air quality criteria needed for dioxins or benzoate BAP, benzoate pyrene, you really need the high vol methods. And I've given the example of Ontario ambient air quality criteria for dioxins and total TEQ and BAP. These really need to be high vols rather than medium volumes or the industrial hygiene to get to those levels. Now, that doesn't mean that that's what your application. The other methods for PAHs, for example, may be applicable for if you're concerned with higher levels of PAHs, which is quite common. But really, if you want the low limits and you're really looking at ambient type quality criteria, the high vol methods are the ones that you really need to use. The second item here is talking about PAHs by TO13A, and the method is kind of ambivalent. It talks about the advantages of using either PUF or XAD2, depending on the PAHs you're monitoring. But over the years, even though it's not been recognized directly in the method, most people use just a combination of a PUF XAD PUF media sandwich for sampling on PAHs. And definitely what we recommend, especially because some of the lower molecular weight PAHs are not well captured by just PUF. Now, similarly, on the TO methods for PCBs, and that's TO4A and TO10A, but this is not recognized in the methods. But the low molecular weight PCBs are not well retained, and it's our belief that although the methods ask only for PUF, that PUF X80 PUF resin sandwiches are recommended if you're concerned about including the low molecular weight PCBs. Now, the next item has to do with field spikes and what is offered. Now, field spikes are generally targets, usually deuterium or C13 labeled targets added to the media before sampling to show that there's not significant losses during sampling. It's always done on the method 23 dioxins for a stack. It's also done on TO9A for stack commonly, but it's not asked for in the PAH and PCB methods. We offer it, we recommend it. It's a minor added expense. Now, the next item has to do with a myth that permeated the industry for a long period of time. And that has to do with the perception that, okay, if semi-volatiles are greatly particulate bound, then why don't we just analyze the filter particulates and we'll get the particulate bound concentrations, and you do the media afterwards, say XAD or PUF, and you'll get the amount, the concentration that is gaseous. Well, it's a myth. It's a myth because the issue of ratio of particulate bound to gaseous has to do with a thermodynamic scenario, and that thermodynamics drives it generally to the particulate bound. But in the case of while you're sampling, you've got filters which have captured particulate, and you're getting gases that pass over those particulates and actually strip the semi-volatiles. That's a kinetic scenario, not a thermodynamic scenario. And so if you analyze the filter separate from the media cartridges, you are not getting a measure of the particulate bound versus the gaseous semi-volatile emissions. So that's another item. Next item below has to do about ECD or air-core pattern matches, which are the methods included in the TO4A and TO10A approaches. They're options that are allowed by those methods. In our opinion, you don't expect air-core matching on air samples. That is, you'll get a differentiation depending on boiling point of what's associated with particulates or not, or what gets put up into the air in the atmosphere. So we definitely do not believe in them. We only support MS methods, both low res and high res for PCBs, where we're doing congener specific, not air-core and pattern match analysis. And one last item, ALS services in North America, we do not generally include ambient nor stack sampling as part of our services. We do the analysis on those samples, but most of that is done by specialists in the industry and by you guys, and we don't really want to compete. Now, that model isn't the model of separate stack testing and ambient testing versus analysis is not universal. There are areas around the world where the same company or even the same laboratory does both, certainly in South America and Pacific Rim. There is now a major stack testing firm, Montrose in the US, well, actually in Canada as well, that also has laboratories. So that's a little bit different. But we maintain the what we believe is the integrity of separate analysis and integrity of samples in that sense. So we don't get involved in both areas. Now I'm going to shift the presentation entirely to what a couple of new areas of stack testing that I see as being hot and emerging. And the first one has to do with perfluorinated targets. And about 5 years ago or so, there was some research done or work done on groundwater levels around a couple of the manufacturing facilities for perfluorinateds. And what they discovered, to their surprise, was that the pattern of groundwater contamination showed that the primary source of that groundwater contamination had to do with rain deposition. And so that realization has all of a sudden put a great emphasis on, okay, what's coming out of these stacks and how far are they being transported and so forth. So stack methods, although there was some work on it, has gone to a much higher priority. The method that I'm going, these are the plethora of targets that we're currently analyzing for perfluorinateds and stack emissions. And the target list for perfluorinateds continues to increase and will continue to increase. So this is I would call a snapshot of what's being offered. Here's a diagram of what I would call as the preeminent train. I say that because other train options have been looked at and are being considered, but this is the one that's gaining favor by Ray Merrill at US EPA. And so this is what I would predict as being the model going forward. And you'll recognize that in general, this design is around the modified method 5 train for semi-volatiles. And again, these are other semi-volatiles. It has one addition, it has another X80 trap after all the impingers to capture some of most volatile of the perfluorinated targets. But this is the train that looks like it's going to take off as far as going forward. I know that this, we have a copy of the draft method. The draft method is about to be officially released soon. And this is what I believe is going to be used typically going forward. Now, at this stage, and I'm going to step back to back in the 80s when semi-volatile trains were first developed, and some of the other trains, where there was an interest in analyzing each of the different fractions that came off the train. So the rinses in this area, the filter, the rinses even down in these sections, the impinger contents, of course, the X8E trap. These were analyzed separately partly to self-validate the methods, but also to get an understanding of what's being captured in the methods. And that's the phase we're in now. So when these trains are being asked for, we're being asked to analyze many different fractions on the train. And I think that'll go on for several years going forward until there's a certain comfort level on these trains. So, and maybe it will go to a single analysis combined on the different fractions going forward in the future. But right now, that's not where we're at. The other area of interest that I see as being a great expansion now and going forward has to do with greenhouse gases and a collection of greenhouse gases, specifically methane. And so you've, I'm sure, been familiar with the capturing methane from landfill gases that's been going on. And the concept, of course, is capturing these emissions or otherwise emissions and using them and putting these back into the natural gas feed lines in order for distribution and use as far as burning and whatever else uses the methane through those systems. Now, this is an example of one of these sources. I don't know whether this is a landfill source, but I can see that there's a motor here driving what looks like a vane pump. So we've got inlet, outlet, or outlet, inlet, and there's a sampling line being done for non-isokinetic sampling off of this from this specific location. And this sort of analysis is increasing. Now, it's not just because of landfills. We're now morphing into another phase. The capture of methane and feeding them back into natural gas feeds is going down to the level of farms and capturing from pig and cattle farms. Of course, the poop associated with that. And they're capturing them and putting them back into the natural gas feeds. So that's why this is really expanding, because it's going to the level of farms. And as I understand it, the companies that are selling these type of capturing units are looking for, say, a cluster of 5 farms in an area, and they'll tap into those 5 farms and then do a capturing into the natural gas grid. And that's what's happening. And the next couple of slides will give you the sorts of analyses that are being done. This work here is being led by Nicole Bryson, sales agent for the Simi Valley Lab. She's really been driving this and has put together great comprehensive packages associated with the industry targets that they're looking for and the concentrations. And that's multiple packages because there's different target lists and different standards that are being done. But this is the first page here is a lot of VOC analyses and other analyses that are being done on these. Siloxanes are really an issue associated with landfill gases. It has to do with polysiloxanes in landfill. When they degrade, they give off some low molecular weight siloxanes, volatile siloxanes, I think CS4 to S8 range. And these are a problem as far as burning and methane is concerned, because when you burn the siloxanes, you get silicon dioxide. These other items, and nitrosodiene-propylamine, other semi-volatiles, pesticides, metals, these are the areas that we're supporting in our lab on this. Metals maybe at our lab or industrial hygiene methods, Salt Lake City. Here's a summary table of one of these type lists, and gives sampling reference methods and instrumental methods. And you see from TO methods to stack methods to ambient to industrial hygiene methods, depending on what is applicable and so forth. So these packages are available through work on Nicole Bryson. Here's an example of one of these, another example of sampling from one of these sources. This is a modified method 29 multi-metals, where there's no filter and it's just impinger captures, small impingers. So overall, in summary, I hope I provided an introduction to ambient and stack methods, and helping you as far as understanding of the terms and what's being done and why, and also given leads into the two areas that I see of hot areas going forward: perfluorinated and natural gas feed sources. So at that, I leave it open for questions.
Thanks, Ron. So yes, we're going to open up for questions now. If the attendees will look on the bottom of their toolbar in Zoom, they'll see a question and answer function, and you can go ahead and submit your questions there, and I can field them to Ron. I'll just give a few minutes for you guys to put in some questions. I don't see any questions so far, but I'll give a couple more minutes. And if you guys also want to use the chat function to submit your questions, that's also fine. I'll just go over some brief notes while we're waiting. This webinar presentation has been recorded. All participants of this webinar will receive a follow-up email once the recording is available to view. We also post our webinars on the ALS Global website and our ALS YouTube channel in the webinar playlist. I encourage you to find a wide range of video resources and past Webinar Wednesday presentations available there. Also, please follow our company page on LinkedIn, as we post announcements and registration links to future webinars and other valuable resources and updates. Okay, it looks like we do have a question from Maurice. He asks, you mentioned PFAS several times. Is this a concern in Ontario?
It's a concern. Can you guys hear me? I hope it is a concern worldwide.
Sorry, we can't. Do you mind moving a little closer to your microphone, Ron?
Sure.
Yep.
PFAS is of concern worldwide. And ALS has been at the forefront of this. Actually, it became, for reasons I'm not clear on, it became most in focus in Australia initially. And so our Australian network was instrumental in development of some of these targets and approaches, and they've launched corporate-wide methods around the world for doing perfluorinateds, and that includes Waterloo in Canada, and in the US, there's ALS Kelso, ALS Holland, and I believe there's another lab that's doing the perfluorinateds in the US as well. So for us, we're not doing the perfluorinated analysis here in our lab, and so we do support the sampling and the extractions, and we send the extracts to our sister lab in Waterloo, and they do the analysis on the extracts.
Okay. Doesn't seem like anyone else has asked any additional questions. So I believe that's it. And I guess we'll just go ahead and close then. Thank you everyone for attending today. Again, you can contact Ron for any questions. His contact details will be in the email following the webinar and along with the recording. I hope everybody enjoys the rest of their week.